close your eyes and imagine the strangest alien world you can. Maybe it's covered in alien jungles, or has purple skies or rings like Saturn. Maybe there are twin suns setting over crystal mountains, like something out of science fiction. Whatever you're imagining, reality is stranger. The universe has spent billions of years creating planets, and it turns out nature has far more imagination than we do. Worlds made of diamond. Planets where glass rains sideways at supersonic speeds. Entire oceans with no land whatsoever. Places so hot that rocks evaporate. Worlds wandering alone through the darkness, between stars. These aren't fantasies. They're real. We've found them. We've studied them. And every new discovery makes our own solar system look increasingly familiar. For decades, we assumed other star systems would be similar, orderly, predictable, maybe different in detail, but built from the same basic ideas. We were wrong, spectacularly wrong. When we began discovering planets around other stars, we expected variations on what we already knew. What we found instead was chaos. Worlds that break our models of planetary formation. Objects so strange that scientists had to invent entirely new categories just to describe them. The universe, it turns out, doesn't care about our expectations. Tonight, we're exploring those worlds, the weirdest, strangest, most mind-bending planets ever discovered. Not the Earth-like ones, not the hopeful candidates, but the true outliers, the cosmic oddities, worlds where molten glass rains from the sky, where carbon is compressed into diamond beneath crushing gravity, where darkness is so complete that light itself seems to disappear. And, perhaps most astonishing of all, the more we look, the more common this weirdness becomes. So let go of what you think you know about planets. Forget the neat diagrams from school. The real universe is far stranger, far more creative, and far more surprising than we ever imagined. Let's gently explore the weirdness. Imagine standing on a world where the sky is a brilliant, deep cobalt blue, the kind of blue that looks almost artificial, like someone photoshopped the heavens. Beautiful, right? The kind of place you'd want to visit. Now imagine that sky is actively trying to kill you. This planet exists, and it's one of the most violently hostile places we've ever discovered. From a distance, through a telescope, it looks stunning. That blue color is real, caused by silicate particles suspended in the atmosphere, tiny grains of glass floating in the air. On Earth, we'd call it beautiful. Here, it's a weapon, because those silicate particles aren't just floating. They're being accelerated by winds that make Earth's worst hurricanes look like gentle breezes. Winds so fast that if you stood in them, you wouldn't be knocked over, you'd be vaporized. And those tiny glass particles? They're moving with those winds, turned into projectiles, slicing through the atmosphere at speeds that would shred anything in their path. It's raining glass, sideways, at speeds faster than sound. It's raining glass, sideways, at speeds faster than sound. But it gets worse. This world is tidally locked to its star, meaning one side perpetually faces the star while the other faces eternal darkness. The day side is scorching hot enough to melt metal. The night side is slightly less hellish, but still uninhabitable. And between these two extremes, winds scream around the planet, carrying that deadly glass rain in an endless, violent loop. The temperature difference between day and night creates a pressure gradient so extreme that the atmosphere is in constant, furious motion. The planet is essentially one giant storm system, never resting, never calming, just endlessly churning in its own private hell. And here's the thing that makes it even stranger. This planet is close to its star, very close. So close that it completes an orbit in just a couple of Earth days. It's being roasted, its atmosphere is being stripped away slowly, and yet it persists, this blue nightmare world, forever locked in its violent dance. If you could somehow survive on the surface, and you absolutely couldn't, you'd see a sun that fills half the sky, never moving, never setting. The horizon would glow with eternal twilight as day transitions to night around the planet's curve. The sky would be that beautiful, terrible blue, and the wind would never stop screaming. This is what the universe creates when left to its own devices. Not the comfortable, temperate worlds of science fiction, but something far more extreme. A planet where beauty and horror are inseparable, where the same atmospheric chemistry that creates stunning blue skies also creates the conditions for supersonic glass storms. Scientists discovered this world by watching it pass in front of its star, measuring how the starlight changed as it filtered through the atmosphere. That's how they detected the silicates, how they measured the wind speeds, how they determined the temperature. They built this picture of hell from photons that traveled across light years of space, carrying information about a world no human will ever visit. And the truly unsettling part? This planet isn't unique. We've found others like it, hot worlds tidally locked to their stars, with extreme winds and exotic chemistries. This type of planet might be common in the universe. The glass rain world isn't an anomaly. It's a category. The universe is full of places that will kill you in ways you never imagined. This planet doesn't need monsters or aliens or cosmic threats. The weather itself is the threat. The sky is the threat. The very air, if you could call that superheated, glass-filled atmosphere air, is lethal. And yet, from a distance, it's beautiful. That brilliant blue, visible across interstellar space, a jewel orbiting its star. You'd never know, just by looking, that you're seeing one of the most violent places in the known universe. That's the lesson of the glass rain planet. The universe doesn't distinguish between beautiful and deadly. Sometimes they're the same thing. And now let's move on to one of the things I found most interesting. What if I told you there's a planet out there made almost entirely of diamond? Not diamond mines, not diamond deposits, the entire planet. A world where the ground beneath your feet, if you could stand on it, would be compressed carbon in its crystalline form. A sphere of diamond floating in space. Your first thought is probably about value. How much would a planet made of diamond be worth? The answer is meaningless. So much that the concept of value breaks down. All the wealth on Earth, all the money ever created, all the economies combined wouldn't be a fraction of what this world represents. It's the ultimate treasure, floating unreachable in the cosmos. But forget the economics for a moment. Think about what this planet actually is, what it means. On Earth, diamonds form deep underground, under intense pressure and heat, carbon atoms crushed and arranged into that perfect crystalline structure. They're rare because those conditions are rare, found only in specific places in the mantle, brought to the surface by volcanic eruptions over millions of years. On this planet, the entire world is those conditions. The pressures are so extreme, the temperatures so high, that carbon doesn't have a choice. It crystallizes. The whole planet is essentially what Earth's core might look like if Earth were made of carbon, instead of iron. But here's where it gets strange. This isn't a cold, glittering diamond sitting peacefully in space. It's a hellscape. The surface, if you can call it, that is likely covered in molten graphite, a scorching ocean of liquid carbon. The temperatures are so extreme that the distinction between solid and liquid blurs. Diamond and graphite, two forms of carbon, exist in layers under crushing pressure at temperatures that would vaporize anything familiar. And there's no beautiful sparkle, no gleaming facets catching starlight. Diamond only sparkles when light passes through it, reflects, refracts. On this world, the surface is too hot, too chaotic. Any light hitting it would be absorbed by the heat, swallowed by the molten carbon seas. Imagine standing there, if you could. The ground beneath you would be harder than anything on Earth, compressed carbon that would make steel look soft. But you'd be standing on an ocean of liquid graphite, waves of molten carbon rolling across the surface, glowing with heat. The sky would be thick with carbon vapor, clouds of the same element that forms the ground, cycling between solid and liquid and gas in an endless, violent loop. Carbon rain might fall, not water, not even glass like the previous planet, but droplets of liquid carbon condensing from the atmosphere. This planet orbits close to its star, baked by radiation, locked in a tight embrace with its sun. The heat keeps the surface molten, keeps the carbon cycling, prevents the world from cooling into the solid diamond sphere you might imagine. And deep inside, under all that pressure, in the core where temperatures and forces exceed anything on the surface, the carbon might be compressed into forms we can't even create in laboratories. Diamond is just one crystalline form of carbon. Under extreme conditions, carbon can arrange itself in ways we're only beginning to understand. The planet's core might be something beyond diamond, beyond graphite, some exotic phase of carbon that exists nowhere else. The weirdest part? This planet probably started as something else. It might have been a gas giant once, something like Neptune, with a massive atmosphere of hydrogen and helium surrounding a carbon-rich core. But over billions of years, orbiting so close to its star, the atmosphere was stripped away. The outer layers boiled off into space, blown away by stellar winds and radiation, leaving only the core behind. What we see now is the skeleton of a dead gas giant, the leftover heart of a world that used to be much larger. It's been cooked, stripped, reduced to its most fundamental element, carbon, and compressed into this bizarre diamond nightmare. There's something almost tragic about it. A planet that could have been majestic, a giant world with rings and moons, reduced to a scorched core. Beautiful in concept, a diamond planet, but in reality, just another victim of the universe's indifference. And it raises an uncomfortable question. How many planets like this exist? How many gas giants are slowly being stripped down to their cores, transformed over eons into these exotic, carbon-rich worlds? How many diamonds are floating out there in the darkness, unimaginably valuable and utterly useless? Because that's the ultimate irony. This planet is worth everything and nothing simultaneously. Worth everything by human standards of value, but worthless in practical terms because we'll never reach it, never mine it, never benefit from it. It exists as a reminder that the universe creates wonders we can only observe, never touch. A planet made of diamond, burning in the light of its star, alone and unreachable. Beautiful in theory, hellish in practice, priceless and worthless. That's the universe for you, full of treasures you can't have and wouldn't want even if you could. Next up are the planets that have declared their independence, the rogue planets. Every planet we've discussed so far, every world we know about, has one thing in common: a star, a sun, a source of light and heat and energy. Planets orbit stars. That's what planets do. It's in the definition, practically. A planet is a thing that goes around a sun, except when it isn't. Out there in the darkness between stars, wandering through the vast empty spaces where no light reaches, there are planets. Worlds with no sun, no orbit, no home. Just cold, silent spheres drifting alone through the void, moving through space on trajectories that will never bring them close to warmth again. These are rogue planets, and they might outnumber the planets that orbit stars. Think about that for a moment. Everything we know about planets, every discovery, every theory, every model is based on worlds that orbit stars. But there might be more planets wandering the darkness than there are stars in the galaxy. An entire hidden population of worlds we can barely detect, invisible against the black, existing in conditions so alien that we struggle to even imagine what they're like. How does a planet become rogue? The most common way is ejection. Imagine a young solar system still forming, with planets jostling for position around their newborn star. Gravity is chaos at this stage. Worlds pull on each other, orbits shift, trajectories change. Sometimes a planet gets too close to a larger neighbor, and the gravitational interaction acts like a slingshot. The smaller world is flung outward, accelerating, its velocity increasing until it exceeds the escape velocity of the system. And then it's free, cast out, orphaned, moving too fast to ever be caught again by its star's gravity, doomed to coast through the galaxy forever on momentum alone. Or maybe it happens later, after the system has settled. A close encounter with a passing star disturbs the delicate orbital balance. Planets that have been stable for billions of years suddenly find their paths perturbed. One gets ejected. The star that gave it birth recedes behind it, growing dimmer and dimmer until it's just another point of light among countless others. Indistinguishable, lost. What would such a world be like? First, the cold. Without a star, without that constant influx of energy, temperatures plummet. Whatever atmosphere the planet had when it was ejected begins to freeze. On an Earth-like world, the air itself would condense, falling as nitrogen snow, as oxygen frost. The oceans would freeze solid, top to bottom, transforming into ice miles thick. Any life that existed on the surface would die immediately, not gradually but in an instant of cosmic catastrophe, as heat vanishes and cold absolute takes over. The darkness would be total. Not night darkness where your eyes adjust and you can see stars and shadows. Total darkness. The kind where you can hold your hand in front of your face and see nothing because there's no light to see by. The only illumination might come from the faint glow of distant galaxies, so dim it's meaningless, or perhaps from cosmic rays striking the frozen atmosphere, creating brief, ghostly flashes that illuminate nothing. The silence would be equally complete. No wind, because wind requires temperature differences and moving air, and the atmosphere is frozen solid. No water sounds, no geological activity that might produce vibrations, just stillness. A dead world, frozen in time, coasting through eternity. But here's where it gets strange, where these worlds transition from merely dead to genuinely eerie. Some rogue planets might not be completely lifeless inside. A planet doesn't just cool from the star's heat. It has internal heat to heat from radioactive decay in its core, heat left over from its formation, heat from the pressure of its own mass. On Earth, this internal heat drives plate tectonics, volcanic activity, the magnetic field. It's why Earth's core is molten despite being billions of years old. A rogue planet would lose its surface heat quickly, but deep inside in the core, that internal heat would persist. And if the planet is massive enough, if it has a thick enough layer of ice or frozen atmosphere acting as insulation, that internal heat might keep a subsurface ocean liquid. Imagine it. A world wandering through the darkness, its surface frozen at temperatures barely above absolute zero, completely dead. But kilometers beneath that frozen shell, in absolute darkness, warmed only by the planet's dying internal heat, an ocean. Liquid water, possibly for billions of years, isolated from the universe, untouched by starlight. Could life exist there? On Earth, we've found life in the deep ocean around hydrothermal vents, places where no sunlight reaches, where organisms survive on chemical energy from the planet's interior. If a rogue planet has subsurface oceans and geothermal activity, the same could be true there. Life in absolute isolation, life that never knew stars existed. Ecosystems that evolved in complete darkness, feeding on chemistry alone, existing in an ocean trapped between ice above and rock below, on a world hurtling through intergalactic space with no destination. And if such life exists, it would never know there are stars, never know there are other planets, never know the universe is anything other than their small, dark ocean. They would live and die in perfect isolation, ignorant of the cosmos, in a prison they don't know is a prison. That's somehow more unsettling than mere lifelessness. A dead world is sad. A living world that will never see light, never escape its frozen shell, never know anything beyond its own small existence. That's existentially horrifying. But whether they harbor life or not, rogue planets are everywhere. We can barely detect them because they emit almost no light, no heat signature we can easily spot. We find them occasionally when they pass in front of distant stars, briefly blocking the starlight, revealing their presence through absence, or through gravitational lensing, when their mass bends the light from background objects. Every detection suggests there are countless more we haven't found. For every rogue planet we've spotted, there might be thousands or millions we've missed, too small or too distant or just unlucky enough to never pass in front of anything we can see. The galaxy might be swarming with them. Between every pair of stars in the vast gulfs of empty space, these dark wanderers might drift by the billions, invisible, silent, alone. Some of them might have once been like Earth, warm, wet, possibly alive, orbiting a sun in a comfortable zone where water flowed and atmospheres were stable. Then catastrophe ejection, and everything ended. The world that might have developed complex life, might have eventually produced intelligence, was cast into darkness before any of that could happen. Or maybe it did happen. Maybe some rogue worlds had civilizations when they were ejected. Imagine that horror. Your planet suddenly flung away from its star, temperatures dropping, the sun shrinking in the sky as your world accelerates outward. Would there be time to adapt? Could a civilization survive the transition from star-warmed world to frozen rogue? Probably not. The catastrophe would be too quick, too total. But the idea haunts, somewhere out there in the darkness, a frozen world with the ruins of cities buried under ice, preserved perfectly by the cold, drifting forever through space. Rogue planets are orphans, wanderers, exiles from the systems that created them, doomed to coast through the galaxy forever, never again knowing warmth or light. They're what happens when gravity's dice roll badly, when orbital dynamics go wrong, when a planet is simply unlucky, and they outnumber the lucky ones. They outnumber the worlds that kept their stars, that stayed in orbit, that had any chance at habitability or life or meaning. Most planets, if these estimates are right, are rogues. Most worlds in the universe exist in darkness, and we're the exceptional planet that kept its star, that stayed in orbit, that has light and heat, and the possibility of looking up and seeing the cosmos. We're the lucky ones. The rogues are the norm. And every time we look at the night sky, between the stars we see, there are worlds we don't see. Dark spheres of ice and rock wandering past us, moving through the same space we occupy, invisible, unreachable, alone. The universe, it turns out, is full of ghosts. It was an interesting planet, and now I'm going to tell you about an even more interesting one. I hope this planet I'm about to talk about isn't so interesting that it keeps you awake at night. If you're ready to hear it, I'll tell you. The Styrofoam planet. Planets are supposed to be dense, heavy. That's what makes them planets. Enough mass pulling inward to crush everything into a sphere. Rock and metal, compressed by their own gravity, are gas giants with thick atmospheres and dense cores. Planets have weight, substance, heft. Except for this one. There's a planet out there that shouldn't be able to exist. Not because it's too hot or too cold or orbiting something impossible, but because it's too light, too puffy, too insubstantial. If you could somehow measure its density, you'd find it's less than cork, less than styrofoam, lighter than materials we use for packaging, lighter than things we literally design to be as weightless as possible. Imagine a planet the size of Jupiter, but with barely a fraction of its mass. A world so bloated, so expanded, that if you could somehow scoop it up and drop it in a cosmic ocean, it would float. Not sink like a normal planet, but actually float like a beach ball on water. This shouldn't be possible. When planets form, gravity is supposed to compress them. The more mass you have, the stronger the gravity, the tighter everything gets pulled together. Gas giants like Jupiter are huge, but they're also massive enough that their own gravity compresses their atmospheres into reasonable densities. They're big, but they're also heavy enough that the bigness makes sense. This planet defies that logic. It's enormous, but barely weighs anything by planetary standards. Its atmosphere has expanded to ridiculous proportions, puffed up like a balloon inflated beyond any reasonable limit. The planet looks like it's been inflated by some cosmic pump and is about to pop. Scientists call planets like this superpuffs or cotton candy planets, which sounds whimsical until you think about what it actually means. It means we don't understand them. It means they break our models of how atmospheres should behave. It means something is very, very strange about how this world works. The problem is gravity, or rather the lack thereof. If a planet is this large, its gravity should be compressing the atmosphere, pulling it inward, increasing density. But this planet's gravity is too weak for its size. The atmosphere just sits there, expanded, diffuse, so spread out that the whole planet has the density of foam. How does this happen? What could create such a bizarre configuration? One possibility is extreme heat. If the planet is being roasted by its star, if the atmosphere is superheated, the gas molecules would be moving faster, bouncing around more energetically, resisting compression. Heat can inflate atmospheres, but most hot planets aren't this puffy. They're hot and dense, not hot and foam-like. So heat alone doesn't explain it. Another possibility is composition. Maybe the atmosphere is mostly hydrogen and helium, the lightest elements, with very little of the heavier stuff that would add mass. But even pure hydrogen atmospheres usually have more density than this. You need something else, some additional factor pushing the atmosphere outward or preventing it from collapsing inward. Some scientists think these planets might have massive, extended envelopes of gas that are slowly evaporating. The star's radiation is heating the outer atmosphere, giving gas molecules enough energy to escape. So the planet is constantly losing mass, shedding its outer layers into space, and what remains is this bloated, puffy envelope that hasn't collapsed yet, because it's in the process of being blown away. In other words, we might be looking at a planet in the act of dying. What we see isn't a stable configuration, but a transitional state, a world being slowly stripped of its atmosphere by its star, caught in the moment before it shrinks down to something more normal. In a few million years, this puffy giant might be a much smaller, denser core, all that excess atmosphere boiled away into space. But that's speculation. The truth is, we don't really know. These planets exist. We can measure their size and mass. We can calculate their ridiculously low densities, but we can't fully explain them. They're anomalies. They challenge our understanding of planetary physics. And here's what makes them even stranger. They're not unique. We've found several of these super-puff planets, all similarly bizarre, all with densities that make no sense. So it's not a one-time fluke, some weird accident of formation. It's a category of planet we didn't predict and don't fully understand. What would it be like to visit such a world? You couldn't land on it because there's no surface. It's all atmosphere, all the way down. You'd descend through layers of increasingly dense gas, but even at the deepest levels, you might never encounter anything solid. Just gas getting thicker and thicker, the pressure increasing gradually as you sink. The sky would be strange. On Earth, the atmosphere is thin enough that you can see the stars, the sun, the black of space beyond. On this planet, the atmosphere is so thick, so extended, that you might be hundreds or thousands of kilometers above what we'd consider the planet and still be surrounded by gas. The sky wouldn't be blue or red or any specific color. It would just be haze in all directions, fog without end. And if you descended deep enough, the pressure would eventually become significant. Not crushing like on Jupiter, this planet's gravity is too weak but noticeable. You'd be surrounded by gas dense enough to feel almost liquid pressing against you from all sides, yet still somehow diffuse, still somehow impossibly light for the volume it occupies. There would be no weather in the traditional sense. Weather requires temperature differences, condensation, precipitation. On a planet with such weak gravity and such an extended atmosphere, thermal gradients would be gentle, winds would be slow. The whole atmosphere might just sit there, slowly rotating with the planet, a vast, still ocean of gas, with no storms, no turbulence, just endless, boring uniformity. But the real weirdness is conceptual. We think of planets as solid or at least substantial. Even gas giants have a sense of theirness. They're massive. They have strong gravity. They dominate their systems. This planet is the opposite. It's almost not there. It's a placeholder, a soap bubble in space, something that exists more as concept than object. And yet it orbits its star just like any other planet. It has a place in its system. It follows Kepler's laws. It behaves like a planet in every way except density. It's just wrong. Wrong in a way that shouldn't be allowed but apparently is. The universe has created a planet made of almost nothing. A world lighter than foam, bigger than Jupiter, existing in defiance of what planets are supposed to be. It's a cosmic joke, a glitch in reality, a reminder that the rules we think govern planetary formation are more like guidelines, and nature will violate them whenever it feels like it. And the most unsettling part? We don't know how many more of these exist. These planets are hard to detect because they're so light they barely tug on their stars gravitationally. We find them mostly through transits, and even then, only if they happen to pass in front of their stars from our perspective. There could be thousands of these foam planets scattered across the galaxy, invisible to us, existing quietly in their impossible configurations. Each one a mystery. Each one a challenge to everything we thought we knew about how planets work. Each one proof that the universe doesn't care about our models, or our predictions, or our sense of what's reasonable. A planet lighter than styrofoam, bigger than Jupiter but less massive than Saturn, existing because the universe said it could, regardless of whether it should. That's the lesson of the superpuffs. Physics allows more weirdness than we imagined. The universe has more tricks up its sleeve than we've discovered. And somewhere out there, right now, a planet the size of a gas giant, but the density of cotton candy is orbiting its star, completely oblivious to the fact that it makes no sense. And honestly, that's beautiful. Not because it's comfortable or explainable, but because it means we still have mysteries. We still have things we don't understand. We still have planets that surprise us. The universe isn't done being weird. Not even close. While you continue sleeping, I'll keep talking about a few more interesting planets. I hope listening to them brings you peace of mind and allows you to learn interesting things even while you sleep. The backwards planet, picture a solar system. Planets orbiting a star, all moving in the same direction, like a cosmic carousel. This isn't random, it's fundamental. When a solar system forms from a spinning cloud of gas and dust, everything inherits that spin. The star rotates one way, and the planets orbit in the same direction because they all came from the same rotating material. It's one of the most basic rules of planetary systems. Everything goes the same way, clockwise or counterclockwise depending on your perspective, but consistent, orderly, predictable, except for this planet. There's a world out there orbiting backwards. Retrograde, astronomers call it. While its star spins one way, this planet orbits the opposite direction. It's doing the equivalent of driving the wrong way on a cosmic highway, moving against traffic, violating one of the fundamental patterns of how solar systems work. This shouldn't happen. It breaks the basic physics of how planets form. When you see a planet in a retrograde orbit, you're not just seeing something unusual. You're seeing evidence of catastrophe. Something went terribly wrong in this system's history. Something violent enough to completely reverse a planet's orbit, to overcome billions of years of angular momentum. to send a world careening in the opposite direction from everything else. The most likely explanation: gravitational chaos. Imagine this planet's early life. It formed normally, orbiting in the same direction as everything else, peaceful and unremarkable. But then another planet, maybe a gas giant, something massive, wandered too close. Two large worlds passing near each other create gravitational havoc. They pull on each other, their orbits perturb, trajectories shift. In the chaos, one planet gets flung into a highly elliptical orbit, swinging far out from the star and then diving back in. Each pass near the star, the planet's orbit gets more and more tilted. Eventually, the tilt becomes so extreme that the planet is essentially orbiting over the star's poles rather than around its equator, and then at some point the orbit flips. The planet that was going one direction is now going the other, retrograde, backwards, forever marked by the violence of its past. Or maybe the catastrophe was even more direct. Maybe this planet was captured, pulled from another system entirely during a close encounter between stars. In the early universe, stars formed in clusters, crowded together, passing close enough to gravitationally interact. A planet in one system could be stolen by another star's gravity, yanked away from its birth star, and captured into a new orbit. But captured planets don't fall neatly into orderly orbits. They arrive with whatever velocity and trajectory they had during the capture event. Sometimes that means a retrograde orbit. The planet was moving one direction when it got caught, and that's the direction it kept, regardless of how its new star spins. Either scenario, gravitational chaos or stellar capture, means one thing: violence. This planet's history is written in its backwards orbit, a permanent record of catastrophe. And here's what makes this unsettling. When we look at our own solar system, everything is orderly. The planets orbit the same direction. Their orbits are roughly circular. It all looks stable, peaceful, like it's always been this way. But that's an illusion. Our solar system was chaotic too, early on. Planets migrated, orbits shifted, smaller worlds got ejected or collided. The nice model of solar system formation suggests Jupiter and Saturn once orbited in resonance, then broke free, causing gravitational havoc that scattered the outer planets. Uranus and Neptune might have switched places. Countless smaller bodies were flown into the sun or ejected entirely. We just don't see evidence of that chaos anymore because the solar system has settled. The violence happened billions of years ago, and what remains is the stable configuration we observe today. But the backwards planet? It's a system that never fully settled. The chaos is still visible in that retrograde orbit, a fossil of violence preserved in motion. What would it be like to live on such a world? If you could somehow exist there, if the planet were habitable, which it almost certainly isn't, you'd notice something strange about the sky. On Earth, the sun rises in the east and sets in the west because Earth rotates one way while orbiting the sun. But on a retrograde planet, depending on the rotation, the sun might rise in unusual directions. If the planet is also tidally locked, one side would eternally face the star while the other faces darkness, just like other close orbiting worlds. But if it rotates independently, the sky's motion would feel wrong, unfamiliar, like the universe is running backwards. Not that anyone would be there to notice. Planets in retrograde orbits are usually close to their stars, hot and hostile, tidally locked or rapidly rotating, bathed in radiation. They're not places for life. They're places that barely survive their own violent histories. But forget habitability. The real question is, how common is this? For a long time, we thought retrograde planets must be rare. Surely most systems settle into orderly configurations. Surely the chaos of formation eventually calms, leaving everything spinning the same direction. We were wrong. We found multiple retrograde planets. Not dozens, but enough to know this isn't a once-in-a-galaxy fluke. Retrograde orbits happen. Gravitational chaos is common enough that a noticeable fraction of planetary systems experience events violent enough to flip orbits. And that tells us something profound about how planets form. We used to think planetary formation was mostly gentle dust, sticking together, gradually building up into larger and larger objects, everything happening smoothly over millions of years. And that's part of the story. But the rest of the story is violence, collisions, close encounters, gravitational battles where planets act like billiard balls, scattering each other, altering orbits, sometimes destroying each other entirely. The final configuration of a planetary system, what we see when we look through our telescopes, is what survived. The stable remnant after eons of chaos. The backwards planet is one of the survivors. It endured the gravitational gauntlet, the close encounters, the orbital perturbations. It's still there, still orbiting, still existing despite its violent past. But it bears the scars. That retrograde orbit is a scar, a permanent mark of trauma. And it makes you wonder about the planets that didn't survive. For every backwards planet we see, how many others were ejected entirely? How many collided with their stars? How many were torn apart by tidal forces or shattered in planetary collisions? The universe is full of ghosts, rogue planets, wandering the darkness, debris fields where worlds used to be, systems that once had more planets than they do now. We see the survivors, the stable systems, the planets that made it through. We don't see the casualties, except sometimes we do. The retrograde planet is evidence of casualties. Somewhere in that system's history, something was destroyed, or ejected, or fundamentally altered. The backwards orbit is proof of violence we can't directly observe but can infer from the aftermath. It's like looking at a battlefield long after the fighting ended. The landscape is quiet now, peaceful even, but the scars remain craters, ruins, things out of place. The backwards planet is a crater, a ruin, a thing out of place in an otherwise orderly system, and it will orbit that way forever. There's no mechanism to flip it back. Once a planet is retrograde, it stays retrograde. The orbit is stable in its own weird way, just as stable as a normal orbit, but forever marked by its past. That's perhaps the most haunting thing. The catastrophe is over. The chaos ended billions of years ago, but the evidence persists, visible in every orbit, obvious to anyone who looks. The planet can't escape its history. It can't heal. It just keeps going backwards forever, like a scar that never fades, like trauma encoded in motion, like a world that will never forget the violence of its youth. The backwards planet is a reminder that the universe's cruelty isn't always immediate. Sometimes it's patient. Sometimes it marks you and lets you survive, but ensures you'll carry the evidence of what happened to you for the rest of your existence. Orbiting backwards, against the flow, wrong way forever. That's not just weird, that's tragic. Imagine a planet where the ground is liquid. Not water, not some exotic chemical rock. Molten stone flowing like oceans, glowing red and orange with heat so intense it would vaporize anything familiar in seconds. This world exists, And it's not volcanic activity or isolated lava flows. The entire surface is molten, a global ocean of liquid rock, churning, convecting, radiating heat into space like a dying ember that never quite cools. On Earth, we have lava flows during volcanic eruptions. Molten rock breaks through the crust, flows briefly across the surface, then cools and solidifies. It's dramatic but temporary and localized. The lava always stops, always hardens, always returns to being solid ground. Not here. Here there is no solid ground. There never will be. The planet is too close to its star, too hot, too bathed in radiation for rock to ever solidify. The surface is permanent lava, a world-spanning ocean of melted stone that has been liquid for billions of years and will remain liquid for billions more. Try to imagine standing there, though you couldn't, though nothing could survive, the horizon would glow. Not like a sunset where the light comes from one direction. This glow would be everywhere, beneath you, around you, radiating from the ground itself. The entire planet is incandescent, hot enough that the rock emits visible light. The sky wouldn't be black or blue. It would be filled with rock vapor. Yes, vapor. The same material that makes up Earth's mountains and continents, here existing as gas, evaporated from the molten surface, rising into the atmosphere like steam from boiling water. Except this isn't water vapor, it's silicon, oxygen, metals, minerals, all the components of rock heated until they become gas. And what goes up must come down. On Earth, water evaporates, rises, cools, condenses into clouds, and falls as rain. The same cycle happens here, but with rock. Rock evaporates from the molten surface, rises through the scorching atmosphere, cools slightly, though cool is relative when everything is thousands of degrees, and condenses into droplets. Rock rain falling from clouds made of vaporized stone, splashing into oceans of lava, completing a cycle that mirrors Earth's water cycle, but in a form so extreme it barely seems real. The clouds themselves would be eerie, not white and fluffy like Earth's water vapor clouds. These would be dense, opaque, made of condensed rock particles, tiny droplets of molten stone suspended in gas. They glow faintly with their own heat, casting a strange, diffuse light across the landscape. And because this planet is tidally locked one side, forever facing its star, the day side is even more hellish than the night side. The eternal sun beats down on that hemisphere, keeping temperatures so high that nothing could even theoretically exist as solid. The lava ocean on the day side might be deeper, hotter, more violently churning as heat from the star drives convection. The night side, perpetually in darkness, would be slightly cooler. And by cooler, I mean temperatures might drop enough that some minerals could potentially solidify near the surface. But even there, the heat from the molten interior would keep most of the surface liquid. You might get temporary crusts of solidified rock forming and then breaking apart, pulled back under by the currents in the lava ocean. Between day and night, where eternal sunset meets eternal midnight, you'd have the terminator zone, the boundary region where conditions transition from unbearably hot to merely impossibly hot. Here, the lava ocean would be turbulent, driven by the temperature difference, with currents flowing from day side to night side and back again, circulating heat, creating storms of rock vapor and lava rain. What kind of weather would such a world have? On Earth, weather is driven by temperature differences. Hot air rises, cold air sinks, moisture evaporates and condenses, creating winds and storms and precipitation. All the same principles apply here, but with lava and rock vapor instead of water and air. You'd have lava hurricanes, massive convection cells in the molten ocean, driven by heat from below and cooling from above, creating vortices of swirling liquid stone. You'd have rock vapor storms, where vast clouds of vaporized minerals sweep across the surface, driven by winds that move at speeds we can't even measure because they destroy any instrument we tried to place there. The tidal forces would be immense. Just as our moon raises tides in Earth's oceans, this planet's star would raise tides in the lava ocean, but these wouldn't be gentle swells. The planet is so close to its star, the tidal forces so extreme, that the lava ocean would bulge dramatically toward and away from the star, creating massive waves of molten rock that circle the planet endlessly. And beneath all this chaos, beneath the lava ocean, there might be solid rock, deep enough where pressures are high enough, even these extreme temperatures might not be sufficient to keep everything molten. The planet's interior might have a solid core crushed by its own gravity into a form we'd recognize as rock. But that core would be divorced from the surface by an ocean of lava potentially hundreds of kilometers deep. There would be no connection between the solid interior and the molten surface. No way for material to exchange. Just two separate realms, solid below, liquid above, never touching, never interacting except through heat transfer. Geologically, this planet is frozen in a state Earth passed through billions of years ago. Early Earth, just after formation, was hot enough that its surface was molten. We'd call it the magma ocean phase, and it lasted for millions of years before the planet cooled enough for a crust to form. This lava world never got to cool. It formed, heated up, melted, and stayed that way. It's locked in Earth's infancy, forever young in the worst possible way. While Earth matured, developed a solid crust, oceans, atmosphere, and eventually life, this planet remained trapped in its molten state, unable to progress, unable to evolve beyond this hellish configuration. And it will stay this way until its star dies. Only when the star expands into a red giant and engulfs the planet, or when the star burns out and the planet finally cools only, then will the lava ocean solidify. Billions of years from now, this world might have a solid surface, but by then there will be no one to see it, no star to illuminate it, just a cold, dead cinder orbiting a stellar corpse. There's something profoundly sad about that. A planet with no future, no possibility of change, no hope of becoming anything other than what it is. It's locked into this state by physics, by its proximity to its star, by the fundamental laws that govern heat and temperature and phase transitions. It can't evolve, can't cool, can't develop. It's stuck. And yet, in its own terrible way, it's beautiful. An entire world glowing like an ember, oceans of lava reflecting starlight, clouds of rock vapor backlit by the heat from below. If you could somehow observe it from orbit, protected from the heat, it would be stunning, a planet-sized coal burning in the darkness, radiating heat and light. Beauty and horror, once again inseparable. The lava world is gorgeous in the way a forest fire is gorgeous, mesmerizing in the way destruction is mesmerizing. You can't look away even though you know what you're seeing is terrible. This is what the universe creates when it places a planet too close to its star. Not habitability, not potential. Just endless, mindless heat, cycling rock between solid and liquid and gas, creating a parody of Earth's water cycle with temperatures that would melt steel. A world where the ground is an ocean and the rain is stone, where clouds glow with their own heat and storms are made of vaporized mountains, where nothing solid exists on the surface and nothing ever will. The lava world is proof that planets can be trapped just like anything else. Trapped by gravity, by temperature, by the cruel geometry of their orbits. Condemned to exist in states that offer no possibility of change, no escape, no future. Just heat, just motion, just an endless churning ocean of molten rock, glowing in the darkness forever. Every planet we've discussed has been hostile in some way. Glass rain, diamond cores, frozen rogues, lava oceans, each one a nightmare variation on what a world can be. But what about water? Water is life, right? Water means oceans, beaches, waves lapping at shores. Water is where life began on Earth. Surely a planet covered in water would be welcoming, habitable, maybe even pleasant? Not quite. There's a planet out there that's entirely ocean. Not mostly ocean like Earth, where continents and islands break up the water. Entirely ocean. No land whatsoever, no beaches, no islands, no mountains poking above the waves. Just water covering the entire surface, extending down into depths that would make Earth's oceans look like puddles. And the deeper you go, the stranger it gets. On Earth, water has one basic form in the ocean, liquid. It stays liquid from the surface down to the seafloor, getting colder and darker, but remaining fundamentally the same substance. Even at the deepest points, it's still water you could swim through, still water that behaves the way water should. On the water world, that's not true. The ocean is so deep, the pressure so immense, that water stops being normal water. It transforms into something else, exotic forms of ice that exist only under crushing pressure and bizarre temperatures. Deep beneath the surface, where the weight of the ocean above creates pressures we can't easily replicate on Earth, water freezes despite being hot. Not because it's cold, but because the pressure forces the molecules into crystalline structures, even at temperatures that would normally keep them liquid. This is called high-pressure ice, and it comes in multiple forms, each with different properties, different structures, different behaviors. Imagine sinking down through this ocean. Near the surface, everything seems normal. Water, clear or murky, depending on what's suspended in it, extending in all directions. The sun, if there is one, if this world orbits close enough to receive light filters down from above, creating those familiar shafts of light you see in underwater photography, but there's no bottom. You keep descending, and the light fades, and the water grows darker, and still there's no bottom. No sand, no rock, no seafloor. Just more water, getting darker and colder and thicker as pressure increases. Eventually, you reach a depth where something changes. The water becomes strange. It's still technically water, still molecules of hydrogen and oxygen, but it's denser, more viscous, behaving less like liquid and more like something between liquid and solid. This is the transition zone where normal water gives way to high-pressure phases. Go deeper and you encounter the first layer of exotic ice, except it's not cold. It's hot, potentially hundreds of degrees above the freezing point we know on Earth's surface. But the pressure has crushed it into a solid despite the heat. You could be at temperatures that would boil water at Earth's surface, and here the water is solid ice. This ice isn't transparent like the ice cubes in your freezer. It might be opaque, dense, arranged in crystalline structures that don't exist naturally on Earth. Some forms of high-pressure ice are denser than normal ice, sinking rather than floating. Others have bizarre properties, conducting electricity, or behaving plastically, deforming under stress rather than shattering. And beneath that layer, if you somehow kept descending, you'd encounter even stranger phases. Ice that's even denser, even more exotic, compressed into configurations that only exist under the most extreme conditions. Layer after layer of different ice types, each one stable only within a specific range of pressures and temperatures, stacked like geological strata, except made entirely of water in its various impossible forms. Eventually, at the very bottom, you might reach rock, the actual rocky core of the planet, small and compressed, buried under an ocean so deep and so massive that the distance from surface to bottom might be comparable to the distance from Earth's surface to its core. But standing on that rock would be impossible. You'd be crushed by the pressure long before you reached it. The water above you would weigh more than anything human-made could withstand. You'd be flattened, obliterated, reduced to paste by the sheer mass of the ocean. So what would life be like on such a world? If life exists, if biology could take hold in this endless ocean, what form would it take? On Earth, ocean life is diverse because oceans have zones, surface regions with light and warmth, deep regions with darkness and cold, transitional zones with different pressures and temperatures. Life adapts to each zone, filling every available niche. On the water world, the same would be true, but more extreme. Surface life would have to cope with the fact that there's no land to crawl onto, no beaches to colonize, no interface between water and air except the ocean's surface itself. Any organism that evolved there would be permanently aquatic, forever swimming or drifting, never resting on solid ground, because solid ground doesn't exist. Deep-sea life would face even stranger challenges. As you descend into the high-pressure zones, into the regions where water becomes exotic ice, the environment would be utterly alien. Could life exist in the boundary regions between liquid water and hot ice? Could organisms tunnel through the ice layers, metabolizing the strange chemistry of compressed water? Maybe. Life on Earth has proven remarkably adaptable. We've found bacteria in Antarctica's ice, organisms in superheated hydrothermal vents, microbes in the crushing depths of the Mariana Trench. Life finds ways to survive in conditions we'd consider impossible. But on the water world, the challenges would be different. There's no sunlight at depth. Photosynthesis wouldn't work except near the surface. There's no volcanic activity to provide heat and chemicals. The ocean is too deep, the rocky core too isolated. Any life at depth would need to survive on chemistry alone, on whatever energy gradients exist in the water itself. And there's the question of nutrients. On Earth, the ocean's food chain depends on organic matter sinking from the surface-dead plankton, whale falls, detritus of all kinds drifting down to feed deep-sea organisms. On a water world with no land and no seafloor within reasonable depth, would this cycle still work? Or would nutrients just keep sinking, accumulating in the exotic ice layers where nothing could access them? Maybe life could only exist near the surface, in the thin shell of liquid water where light penetrates and photosynthesis is possible. Below that, an empty abyss, lifeless despite being filled with water, too deep and too strange for biology to colonize. Or maybe we're thinking too narrowly. Maybe life on the water world wouldn't be limited to the surface. Maybe organisms would evolve to navigate the entire water column, migrating between zones, exploiting the chemistry at different depths, thriving in conditions we'd consider sterile. The unsettling part is this: if you were somehow on this planet's surface, floating in the ocean, there would be no horizon, just water extending to the edges of the visible world. No mountains in the distance, no islands, no variation in the landscape except waves. You could swim forever in any direction and never find land, never find anything except more water. The psychological effect would be maddening, an endless, featureless expanse with nothing to orient yourself, nothing to mark your position except the sun or stars above. Imagine shipwrecks on such a world if intelligent life existed there. On Earth, shipwrecks eventually sink to the seafloor, coming to rest on sand or rock, becoming artificial reefs. On the water world, a sinking ship might descend for weeks, months, slowly falling through darkness, through pressure zones, through the transition to exotic ice, until it finally embeds itself in one of those strange ice layers or reaches the distant rocky core. The wreck would be unreachable, unrecoverable, lost forever in a depth that makes Earth's ocean trenches look shallow. Any civilization on the water world would be unable to salvage their losses, unable to recover anything that sinks beyond a certain depth. The ocean would be a hungry mouth, swallowing everything and returning nothing. And yet, despite the strangeness, despite the alienness, the water world might be habitable. If the planet is in the right orbit, at the right temperature, with the right atmospheric composition, life could thrive there. Not human life, we need solid ground, dry land, air to breathe. But something could live there. Something adapted to the eternal ocean, comfortable in the endless water, never missing the land it never knew existed. That's perhaps the most fascinating thing. A water world would be utterly alien to us, completely unsuitable for human colonization, and yet it might be teeming with life. Just not life we'd recognize. Not life that looks like Earth's ecology. Something else, something that evolved in permanent wetness, that knows nothing but ocean, that has no concept of land or shore or solid ground. A water world is a reminder that habitability doesn't mean human-friendly. It means capable of supporting life, any life by any means. And life, as we've learned, is far more flexible than we are. We need specific conditions, dry land, breathable air, moderate temperatures. Life in general. Life can adapt to almost anything. So the water world might be paradise for some hypothetical organism perfectly suited to it. For us, it would be a prison, an infinite ocean with nowhere to stand, nowhere to rest, nowhere to be except floating in water that extends forever down. Beautiful, probably. Habitable, possibly. But home? Never. Because no matter how much we might romanticize oceans, no matter how much we love water, we're land creatures. We need something solid beneath us, something that doesn't move, something we can build on. The water world has none of that. Just water all the way down, until it's not water anymore but something stranger, an entire planet of ocean and nowhere to stand. That's not hell, exactly, but it's not heaven either. It's just alien, profoundly, completely alien. Planets reflect light. That's how we see them. Light from their star bounces off their surface or atmosphere and travels to our eyes or telescopes. Even dark objects reflect some light enough that we can see them, enough that they're visible against the black of space. Except for this one. There's a planet out there that's darker than coal, darker than asphalt, darker than the darkest paint humans have ever created. It absorbs almost all the light that hits it, reflecting virtually nothing back into space. If you could somehow see it with the naked eye, it would be a void, a circular absence in the star field, a hole where a planet should be. This shouldn't be possible. Planets have atmospheres, surfaces, clouds, all things that reflect at least some light. Even the darkest objects we know reflect a few percent of incoming light. That's just how matter works. Atoms interact with photons. Some photons get absorbed, others bounce away. That's reflection. But this planet breaks the rule. It's black. Truly, deeply, impossibly black. Scientists call it the darkest planet ever discovered, and they're not exaggerating. When they measured how much light it reflects, they found it absorbs more than 99% of the light hitting it. For comparison, Earth reflects about a third of incoming light clouds, oceans, ice, all bouncing photons back into space. Even Mercury, which has no atmosphere and a dark, rocky surface, reflects more than 10%. This planet reflects less than 1%. It swallows light. It's a gravitational trap for matter and a literal trap for photons. What could make a planet this dark? What material, what atmospheric chemistry could absorb light so completely? We don't fully know. The planet is a gas giant, orbiting extremely close to its star, tidally locked with one side facing the star eternally. Its atmosphere is superheated hot enough to vaporize metals, hot enough that exotic chemistry dominates. And somewhere in that chemistry, there's something that makes the planet black. One hypothesis involves clouds. Not normal clouds, exotic clouds made of vaporized materials that only exist at extreme temperatures. Sodium vapor, potassium, titanium oxide. These compounds can form particles that absorb light across many wavelengths, trapping photons rather than reflecting them. But even that doesn't fully explain the extreme darkness. Most materials, even dark ones, reflect some light. To absorb this much, the atmosphere would need to be perfectly optimized for light absorption, the right chemicals, the right particle sizes, the right distribution, all combining to create an almost perfect black body. It's as if the planet is trying to disappear, as if it wants to be invisible. And in a way it almost is. When this planet transits its star passing between the star and Earth, it creates a dip in the star's brightness that's barely detectable. Most planets block a noticeable amount of light during transit. This one blocks light, but it doesn't add much of its own reflected light to the measurement. It's there, but barely. From the planet's surface, if it has a surface, if you could somehow stand in its atmosphere, the experience would be surreal. The star would dominate the sky, enormous and bright, filling half the visible heavens. You'd be bathed in starlight, blinded by the intensity, but everything else would be dark. The ground or the clouds below you would absorb the light rather than reflecting it. There would be no scattered light, no diffuse glow, no secondary illumination. Shadows would be absolute, perfect blackness. Anything not directly lit by the star would be invisible. It would feel like standing under a spotlight in an infinite void. The star illuminates you, but nothing else. The planet around you swallows light, refuses to scatter it, leaves everything beyond the star's direct beam in perfect darkness. And on the night side, The hemisphere facing away from the star, locked in eternal darkness, the blackness would be complete. No starlight reaches there. The planet itself doesn't glow, doesn't emit visible light despite being hot, just darkness. Absolute, unbroken darkness. Except there's one thing, one tiny anomaly in all that blackness. The planet does emit a faint glow. Not much, barely detectable, but it's there. A dull red light coming from the planet itself caused by its extreme heat. The atmosphere is so hot that it radiates in the infrared and just barely into the visible spectrum. If you were on the night side, your eyes dark adapted, you might see the faintest red glow around you, like the dying embers of a fire. But that glow wouldn't be enough to see by. Not enough to illuminate anything. Just enough to remind you that the darkness isn't complete, that the planet has thermal energy even if it won't reflect light. The weirdness of this world isn't just its color. It's what that color represents, a combination of chemistry, temperature, and pressure that creates conditions unlike anywhere else. The darkness is a symptom of the planet's extremity, a visible consequence of invisible processes, and it raises questions. If a planet can be this dark, what else is possible? Could there be planets even darker, absorbing every single photon, reflecting nothing whatsoever? Could there be worlds that are invisible, not because they're far away, but because they refuse to be seen? The universe already has dark objects, black holes, which trap light gravitationally. But this planet does it chemically, through atmospheric composition and temperature. It's not a gravitational trap, but an electromagnetic one, a place where photons go to die, and there's something unsettling about that. We navigate the universe by light. We see things because they reflect or emit photons. Objects that don't interact with light are invisible to us, undetectable except through their gravitational effects. This planet is almost that. Almost invisible, almost absent, a ghost world that barely admits it exists, hiding in its own shadow. Scientists discovered it only because it orbits a star we were already watching. If it were a rogue planet wandering through interstellar space, we'd never find it. It would be invisible against the black, darker than the background, undetectable by any telescope. How many more are out there? How many dark planets exist in the galaxy, absorbing light, hiding in plain sight? We wouldn't know. We couldn't know. They could pass within light years of Earth, and we'd never notice. The pitch-black planet is a reminder that the universe contains things we can't see. Not just distant things or small things, but objects that actively avoid detection, that have properties making them nearly impossible to observe. And if planets can be this dark, what about smaller objects? Asteroids, moons, debris? Could there be dark matter, not the hypothetical particle physicists search for, but actual matter, actual objects that don't reflect light, that exist invisibly throughout the galaxy? Probably not. Most objects don't have the right chemistry to absorb light this completely. But the fact that it's possible at all that nature can create planets this dark means we should be humble about what we think we can see. The universe might be fuller than it appears, populated with objects we can't detect, hiding in darkness not because they're far away, but because they're fundamentally difficult to see. The pitch-black planet is one we happened to catch during transit, one that gave itself away by blocking its star's light. But how many others are out there, untransiting, unobserved, invisible? We don't know, can't know. The darkness hides them. And somewhere in that darkness, orbiting stars we've never noticed, there might be worlds darker than coal, blacker than space itself, existing in a state of near invisibility, silent, hidden, unknown. The universe keeps its secrets, and some of those secrets are written in darkness we can't penetrate. The pitch-black planet is one we found by accident. How many remain unfound? All the planets we've discussed orbit living stars. Stars burning hydrogen, fusing elements, radiating energy into space. Active, dynamic objects that will shine for billions of years before exhausting their fuel. But there are planets that orbit dead stars. And death, in this context, doesn't mean peaceful fade into darkness. It means violence, catastrophe, explosion. A pulsar is what remains after a massive star dies a neutron star, the collapsed core left behind when the star's outer layers explode in a supernova. Its matter compressed to densities that defy intuition, crushed by gravity so extreme that atoms collapse. Electrons merge with protons, leaving only neutrons packed together in a sphere the size of a city, but with more mass than the sun. And this dead star spins incredibly fast, multiple times per second. As it spins, it emits beams of radiation from its magnetic poles, radio waves, X-rays, gamma rays, sweeping across space like a cosmic lighthouse. When those beams pass over Earth, we detect regular pulses, hence the name, pulsar. This is one of the most extreme environments in the universe. Magnetic fields billions of times stronger than Earth's. Radiation so intense it would sterilize anything within vast distances. Gravitational forces that would tear apart anything that came too close. And somehow, impossibly, there are planets orbiting one of these things. This shouldn't be possible. When a star goes supernova, it doesn't just explode, it obliterates. The shock wave tears through the system, vaporizing anything nearby, ejecting planets, destroying moons. Any world orbiting that star should be gone, blasted into atoms, scattered across light years of space. Yet these planets exist. We've detected them. Multiple worlds orbiting a pulsar, in stable orbits, persistent despite the violence that created their current home. How? One possibility, they formed after the supernova. The explosion left behind debris gas and dust swirling around the neutron star. Over time, that debris could coalesce, forming new planets from the ashes of the old system. These would be second-generation worlds, born from destruction, composed of material forged in the supernova itself. Another possibility, they survived. Maybe these planets were far enough away, far enough out in the system that they weren't destroyed during the explosion. The shock wave battered them, stripped their atmospheres, scorched their surfaces, but didn't obliterate them. They endured, traumatized but intact, captured into new orbits around the neutron star remnant. Either way, these are worlds defined by catastrophe. If they're survivors, they remember the explosion, or would, if planets could remember. If they formed after, they're built from the corpse of their former star, composed literally of supernova debris. And now they orbit a dead thing, a stellar corpse that spins and pulses and radiates, hostile and alien, nothing like the warm star they once knew or that once existed here. What would it be like on such a world? First, the radiation. Pulsars emit beams of energy across the electromagnetic spectrum. If you were on one of these planets, you'd be bathed in radiation every time the beams swept over you. Not constantly, pulsars are directional, their beams narrow, but regularly, rhythmically, like a metronome of death. Each pulse would deliver a dose of radiation lethal to any life we know. X-rays, gamma rays, particle radiation, all of it slamming into the planet's surface multiple times per second, sterilizing anything exposed, breaking apart complex molecules, rendering the surface utterly hostile to biology. If the planet had an atmosphere once, it's probably gone now, stripped away by the radiation and the supernova shockwave. What remains would be a bare, scorched rock, surface cratered and irradiated, glowing faintly in the dark from induced radioactivity. Because there's no light. Pulsars don't emit visible light the way stars do. They're too small. Two cool neutron stars are hot, but their surface area is tiny, so the total visible light output is negligible. The pulsar planets orbit in darkness, illuminated only by the faint glow of the neutron star and the regular flashes of radiation. You'd see the pulsar, if you could survive there, a small, dim object in the sky, barely visible, unimpressive to look at, until the pulse hits. Then, for a fraction of a second, the planet's surface would light up not with visible light, but with radiation your eyes can't see, but your cells would feel as they were destroyed. If you could somehow perceive the radiation, each pulse would be a flash of invisible fire sweeping across the landscape, deadly and precise. And the rhythm would be perfect. Pulsars are the most regular clocks in the universe, more precise than atomic clocks, pulsing with such exactness that astronomers use them as cosmic timekeepers. The pulsar planet would experience these pulses forever, each one identical to the last, each one marking time with inhuman precision. It's eerie, like a heartbeat, but mechanical. Like a lighthouse, but lethal. The pulsar doesn't care that planets orbit it. It just spins and pulses, utterly indifferent, a dead star performing its function without purpose or awareness. The planets themselves would be strange. If they survived the supernova, they'd be ancient, battered, scarred by the explosion. If they formed after, they'd be young, but built from exotic materials elements created in the supernova, heavy metals and rare isotopes, things that don't exist in normal planets. Some of these elements would be radioactive, decaying slowly, adding their own radiation to the environment. The planets would glow faintly in the infrared, not from starlight, but from internal radioactivity, from the heat of their own decay. And the orbits would be strange too. Supernova explosions aren't symmetrical. The shock wave doesn't expand evenly in all directions. Planets that survived would have had their orbits perturbed, shifted, altered by the explosion. The current orbits might be highly elliptical, tilted, weird configurations that reflect the violence of their past. If these planets formed after the supernova, their orbits might be more regular, but the formation process itself would have been chaotic. Debris swirling around a neutron star, colliding, accreting, slowly building into worlds, while bathed in radiation and gravitational extremes. Either way, these are planets born from death. They orbit a corpse. They exist in the aftermath of one of the universe's most violent events. Everything about them is a consequence of catastrophe, and there's something deeply unsettling about that. Planets are supposed to orbit living stars, objects that provide light and heat and energy. These planets orbit something that provides only death radiation, without warmth, pulses without life, regularity without purpose. If you stood on the surface of a pulsar planet, protected somehow from the radiation, insulated from the hostility, the sky would be wrong. No sun, no warmth. just a dim point of light that pulses rhythmically, each pulse a reminder of what this place is, what it orbits, what it will always orbit. The silence between pulses would be absolute. No wind, no atmosphere to carry sound, just emptiness, and then the pulse, and then emptiness again, over and over, forever. It's like being trapped in a nightmare where the monster's heartbeat is the only sound, where you can hear it getting closer with each pulse, but it never actually arrives. Except the monster isn't coming, it's already here. You're orbiting it. You're caught in its gravitational grip, and there's no escape. The pulsar planets are a reminder that the universe doesn't clean up after itself. When a star dies, when violence happens, the aftermath persists. Planets remain or reform, orbiting corpses, existing in conditions no life could tolerate, trapped by gravity and systems that should be empty. They're monuments to catastrophe, memorials to the star that died, gravestones orbiting a tomb, and they'll orbit that way forever. The pulsar will spin for billions of years, slowly losing energy, gradually slowing down, but never stopping completely. The radiation will persist. The pulses will continue, and the planets will remain locked in their orbits, bound to their dead star, unable to escape. Imagine being trapped like that, bound to something dead, something that only takes and never gives, something that exists without living, spinning and pulsing in perfect mechanical rhythm while you orbit helplessly forever. That's not just a hostile environment. That's a cosmic horror story. Planets that survive the end of their world only to find themselves prisoners of what remained. The pulsar planets shouldn't exist. The fact that they do is both fascinating and deeply disturbing. They're proof that even in the aftermath of ultimate destruction, matter persists. Planets endure. Orbits continue. But they're also proof that survival isn't always mercy. Sometimes what remains after catastrophe is worse than being destroyed would have been. These planets survived, but they're trapped in hell, orbiting a corpse that will never die completely and never live again, pulsing, radiating, spinning forever. We've visited worlds of glass rain, diamond cores, endless oceans, and radiation-drenched orbits. We've seen planets that shouldn't exist, that break our models, that defy our understanding of what's possible. But nothing compares to this. There's a planet out there that's hotter than most stars. Not hotter than its own star, that would be impossible, but hotter than the vast majority of stars in the universe. Hotter than red dwarfs. Hotter than orange stars. Hot enough that if you could somehow transport this planet into our solar system and place it where Mercury orbits, it would be the second brightest object in our sky. This planet glows, not reflected light its own light. Thermal radiation so intense that the planet emits visible light, glowing white-hot like metal in a forge. From space, it would look like a small star itself blazing against the darkness. The temperature is so extreme that molecules can't exist on the day side. Not complex molecules, not simple molecules, nothing. The heat tears chemical bonds apart. Water would be ripped into hydrogen and oxygen. Carbon dioxide would split into carbon and oxygen. Even molecular hydrogen, the most stable, simple molecule, gets dissociated into individual atoms at these temperatures. The atmosphere isn't made of compounds. It's made of loose atoms, a plasma of disassociated elements, so hot that chemistry itself stops working. On Earth, we have chemistry. Atoms bond together, forming molecules, which interact to create more complex structures. That's how everything works: life, weather, geology, all of it depends on atoms forming stable bonds. On the hell planet, there are no stable bonds on the day side. Just naked atoms colliding at supersonic speeds, too energetic to stick together. The planet exists in a state beyond chemistry, in a realm where only physics applies, and it's not stable. The planet is being destroyed. Slowly, inevitably, it's evaporating. The star's radiation is so intense and the planet is so close that the atmosphere is being stripped away. Atoms on the day side get heated until they exceed escape velocity, flying off into space in a constant stream. The planet is trailing a comet-like tail of its own atmosphere, leaving a glowing trail of lost material as it orbits. If you could see this planet from a distance, you'd see not just a bright point of light, but a streak, a tail of incandescent gas streaming behind it, material fleeing the planet's gravity, never to return. The planet is bleeding atmosphere into space, and it can't stop. This is planetary death in slow motion. Not catastrophic like a supernova, not sudden like ejection into interstellar space. Just a slow, relentless evaporation, the planet shrinking year by year, century by century, millennium by millennium. Eventually, billions of years from now, the atmosphere will be gone completely. What remains will be the core, a small, dense remnant, maybe rocky, maybe something stranger, stripped of everything that made it a gas giant. It will be a skeleton, the leftover corpse of a world that used to be much larger. But for now, it's still dying, still bright, still screaming its death into the void in the form of evaporating atoms. What would the surface be like? There is no surface in the traditional sense. It's a gas giant, all atmosphere down to the core. But imagine descending through it. Imagine falling through this hellscape. Near the top of the atmosphere, where the temperature is merely thousands of degrees instead of tens of thousands, you might find some molecules, simple ones, unstable, existing briefly before being torn apart. The sky would glow, not blue or red, but white, incandescent, like being inside a light bulb. Go deeper and the heat increases. The glow becomes brighter, more intense. The atoms around you are moving so fast they're creating shock waves, sonic booms at the molecular level, a roar of thermal chaos that would be deafening if sound could propagate through this superheated plasma. The pressure increases as you descend, but unlike normal atmospheres where pressure means density and stability, here it just means more violence. More atoms colliding, more energy. The deeper you go, the hotter it gets, until you reach temperatures that would vaporize any material we know. And somewhere deep inside, there might be a core, something solid, compressed by the weight of the atmosphere, hot enough to glow, but stable enough to maintain structure. What that core is made of, we don't know. It's buried under layers of plasma, unreachable, unknowable. The day side of this planet is unimaginably hostile, but the night side, tidally locked, facing away from the star, is slightly less hellish, only slightly. The heat from the day side circulates around the planet, driven by massive atmospheric winds. The night side is cooler, maybe cool enough for molecules to exist, for chemistry to function. But even there, the temperatures are extreme. Hot enough to melt rock. Hot enough that iron would be liquid. The cool side of the hell planet is still hotter than any natural environment on Earth. And the wind, the temperature difference between day and night, creates pressure gradients so extreme that the atmosphere moves at supersonic speeds. Winds that would make Earth's hurricanes look like gentle breezes carrying atoms and heat and energy around the planet in an endless, violent circulation. The Hell Planet is a world in constant motion, constant flux, constant agony. Nothing is stable. Nothing is calm. It's a maelstrom of heat and light and violence, orbiting so close to its star that the two objects are almost touching. The orbital period is measured in hours. The planet whips around its star faster than Earth rotates on its axis, locked in a tight embrace with the object that's killing it. And with each orbit, it loses more atmosphere. With each pass, it evaporates a little more. With each year, it shrinks. There's something tragic about this. The planet isn't doing anything wrong. It's not responsible for its orbit. It formed or migrated into this position through natural processes, and now it's paying the price, slowly being consumed by the star it orbits, unable to escape, unable to cool, unable to do anything but evaporate. It's a prisoner executing itself, condemned not by intention but by physics. The gravity that keeps it in orbit is the same gravity that prevents it from leaving. It's trapped, and the trap is killing it. And the star doesn't care. Stars don't have intentions or awareness. The star just exists, radiating energy, following the laws of nuclear fusion. It's not trying to destroy the planet. It's just there, blazing away, indifferent to what orbits it. The Hell Planet is what happens when a world ends up in the wrong place. Not destroyed quickly, mercifully, but slowly consumed over eons, bright and beautiful in its death, glowing like a beacon of cosmic horror. Scientists discovered this planet through transits and through its own light. It's so bright that we can detect its glow directly, not just reflected starlight, but thermal emission from the planet itself. It contributes measurably to the total light output of its system. When it passes behind its star, a secondary eclipse, the system's brightness drops noticeably because the planet's light is blocked. A planet so hot it acts like a star. A world so extreme it exists beyond the boundaries of where planets should survive. And yet it does survive, for now. It's still there, still glowing, still orbiting, still evaporating. It will continue this way for billions of years, long enough that the timescale becomes meaningless, long enough that its death is effectively eternal, even though it's technically temporary. This is the ultimate hostile planet. Not hostile because of what it has: no glass rain, no lava oceans, no exotic ice. Hostile because of what it is: pure heat, pure energy, pure violence. If hell exists in the physical universe, if there's a place that embodies ultimate suffering and destruction without mercy, it's here. It's this planet, glowing white-hot, tearing itself apart, trailing its own atmosphere into space like a comet made of its own corpse. The Hell Planet is a warning, a demonstration of what the universe can do to worlds unlucky enough to be in the wrong orbit. It's proof that planets can be destroyed not through collision or ejection, but through simple, relentless heat. And somewhere in the galaxy right now, this planet is blazing, brighter than it should be, hotter than stars, dying slowly, beautifully, horrifically, a hell made real, a nightmare given physical form, the ultimate extreme, the final boss of hostile planets. And it will continue glowing, continue dying, continue screaming its thermal death into the void until there's nothing left but a small, dead core and a cloud of escaped atoms spreading through space, a testament to the universe's capacity for cruelty, a reminder that physics has no mercy. The Hell Planet, where even atoms can't survive, where the planet itself is the fuel being burned. That's not just extreme, that's beyond extreme. That's the edge of what's physically possible. And it's real, so here we are. We've visited worlds where glass rains sideways at supersonic speeds. Planets made of diamond burning under molten graphite seas. Rogue worlds wandering through darkness, carrying hidden oceans in their frozen depths. Planets lighter than foam, denser than anything we can imagine, darker than coal, hotter than stars. Each one stranger than the last. Each one impossible until we found it. Each one proof that the universe has more imagination than we do. And here's the uncomfortable truth. Our solar system is boring. Look at what we have. Rocky planets close to the sun, gas giants farther out, some moons with ice, a few asteroids. Everything is orderly, predictable. The planets orbit in roughly the same plane, moving in the same direction. Their orbits are nearly circular. Nothing is dramatically tilted or retrograde or chaotic. It's peaceful, stable, safe. And compared to what we've discovered out there, it's incredibly, almost suspiciously normal. We thought our solar system was the template. We assumed other stars would have similar arrangements, maybe smaller versions of Jupiter, maybe more rocky planets, but fundamentally the same types of worlds in similar configurations. We expected the universe to be orderly because our corner of it is orderly. We were so wrong. The first exoplanet discoveries shattered that assumption immediately. Hot Jupiter's gas giants orbiting closer to their stars than Mercury orbits the Sun. This shouldn't happen. Gas giants form far from stars, where it's cold enough for ice to exist. They're not supposed to migrate inward. Yet there they were, huge planets whipping around their stars in orbits measured in days. And it just got weirder from there. Super-Earths, a planet size that doesn't exist in our solar system. Mini Neptunes, also absent here. Lava worlds, water worlds, diamond planets, rogue planets. Every new discovery added a new category, a new type of world we hadn't predicted and didn't understand. The universe, it turns out, doesn't follow our rules. It doesn't care about our models of planetary formation. It creates whatever physics allows and whatever combinations are possible, regardless of whether they make sense to us. And we've barely started looking. We've found thousands of exoplanets, which sounds like a lot until you remember there are hundreds of billions of stars in our galaxy alone. We've examined a tiny fraction, a statistical sample so small it's almost meaningless. What else is out there? What other varieties of planets exist that we haven't discovered yet? What combinations of chemistry and temperature and pressure create worlds we can't even imagine? Maybe there are planets with atmospheres of metallic hydrogen where the air itself is a liquid metal. Maybe there are worlds with cores of exotic matter compressed into states that don't exist in laboratories. Maybe there are planets where the surface is an ocean of supercritical fluids, neither liquid nor gas, but something in between. Maybe there are planets we'll never detect because they're too dark, too small, too far from their stars. Maybe there are entire categories of worlds that orbit in configurations we haven't thought to search for. The weirdest planets we've found might not be the weirdest that exist. They might just be the weirdest we've noticed so far. And that's both exciting and humbling. Exciting because it means discovery is endless, that we'll keep finding surprises, that the universe will keep proving it's stranger than we thought. Humbling because it means we understand less than we believed, that our models are incomplete, that nature is more creative than our theories. Every weird planet is a gift, in a way, a challenge to our assumptions, a puzzle that forces us to think differently. The glass rain planet teaches us about atmospheric dynamics under extreme conditions. The diamond planet teaches us about planetary cores and what happens when gas giants are stripped. The rogue planets teach us about orbital dynamics and ejection mechanisms. Each discovery expands what we know is possible. Each weird world redraws the boundaries of planetary science. And the best part? We're living in the era of discovery. For all of human history, planets meant the handful of worlds we could see in our own solar system. Mercury, Venus, Mars, Jupiter, Saturn. That was it. That was the entire catalog of known planets. Then, in the span of a single human lifetime, we went from knowing a few planets to knowing thousands. From assuming planets were rare to knowing they're everywhere. From thinking our solar system was typical to realizing it's the exception. Future generations will grow up knowing that planets are common, that most stars have them, that the galaxy is crowded with worlds. They'll learn about hot Jupiters and super-Earths and ocean worlds as naturally as we learned about the solar system's planets. What seems amazing to us will be normal to them, but they'll have their own amazements. Better telescopes, more sensitive instruments, dedicated missions to exoplanets, maybe even probes sent to nearby systems, returning data from worlds we can currently only observe from a distance. They'll discover planets even weirder than the ones we've found. They'll expand the catalog even further. They'll push the boundaries of possible until those boundaries dissolve completely. And maybe, just maybe, they'll find life. Not on the weird planets we've discussed, not on worlds too extreme for biology, but somewhere in the vast catalog of exoplanets on a world we haven't discovered yet. In conditions we didn't expect, life might exist. Or maybe not. Maybe life is rare, confined to Earth, a unique accident that happened once and never repeated. That would be an answer too. Not the answer we hoped for, but significant nonetheless. Either way, the search continues. The discoveries accumulate. The universe reveals itself slowly, one weird planet at a time. And we watch and wonder and try to understand. Because that's what we do. That's what makes us human. We look at the cosmos and ask questions. We find planets stranger than fiction and try to explain them. We push against the boundaries of knowledge, expanding what we know even as we realize how much we don't know. The weirdest planets we've discovered are real. They exist right now, orbiting distant stars, being themselves in all their bizarre glory, glass raining sideways, lava oceans churning, rogues wandering through darkness, worlds dying and being born and existing in states we barely comprehend. And they're beautiful, not despite their weirdness, but because of it. Because they show us that the universe is more than we imagined, stranger than we predicted, more creative than we dreamed. Our solar system is calm, orderly, boring, and that's fine. That's what allowed us to exist, to evolve, to develop intelligence and build telescopes, and discover all those weird worlds. But out there, beyond our comfortable corner of the galaxy, the universe is wild, chaotic, endlessly creative. Building planets that shouldn't exist but do, creating worlds that break every rule we thought was fundamental. That's the lesson of the weirdest planets. The universe doesn't owe us explanations. It doesn't have to make sense. It just has to exist, and it does in ways more strange and wonderful than we ever imagined. So we keep looking, keep discovering, keep being amazed, because the universe isn't done surprising us, not even close. And honestly, that's the best news we could ask for, that there's still mystery, still wonder, still planets out there weirder than anything we've found yet. The universe is stranger than we think, stranger than we can think, and thank God for that.